Public lecture video I attended was about special relativity, and it was given by Professor John DePillis from the Department of Mathematics at the University of California, Riverside. Some of the key concepts that Dr. DePillis discussed are as follows. When dealing with special relativity, linear algebra is the language that can be used to better understand what's going on and relate the principles of special relativity. The laws of physics are equally valid in all frames of reference. The speed of light is the same for all observers, regardless of the motion of the source or receiver. Also, stationary or moving, the observer's speed doesn't matter. Furthermore, wave speed is independent of the speed of the source. Another key concept discussed was inertial frames of reference, or inertial frames. Some properties of inertial frames are: all frames are identical when at rest. Observers within any frame are fixed. Communication between frames are only via perpendicular line of sight. All pairs of frames are synchronized at zero, and relative speeds between frames are negative symmetric. To give examples of special relativity in practice and to highlight some of the key ideas discussed, Dr. DePillis discussed the bug rivet paradox, slinky message transmission, and the twin paradox. Personally, I found the twin paradox to be particularly interesting, and thus will be giving a brief overview of that right now.
Einstein's twin paradox states that if two twins separated at birth, one standing on Earth and another immediately placed on a spaceship heading out to space at roughly 8/10 the speed of light, and then returning to Earth exactly halfway in the middle of its trip, the twin on Earth will be 50 years old when the twin on the spaceship returns home. However, the twin on the spaceship will be only 30 years old, a fraction of the age of the twin on Earth. To understand this, we've used a Minkowski diagram to discuss. At this Minkowski diagram, the twin standing stationary on Earth would travel simply up what we observe as the y-axis, whereas the twin in outer space would go out and come back in. Thus, as you can see, by looking from the twin on Earth at the twin in outer space and vice versa, the age difference is apparent. Thus, this is what accounts for the 20-year age difference after the observed 50 years by the twin on Earth. Thus, the twin from outer space is only 30 years old when he returns, whereas his twin counterpart is 50 years old.